Welcome to The Explainer. Today, we are literally cracking open the programmer's toolbox to see exactly how simple, everyday physical concepts dictate the architecture of complex digital memory. Because, if you've ever wondered why one app feels lightning fast and another just kind of chugs along, well, the secret is entirely in the structure. Organizing data efficiently is the absolute core of writing fast, functional code. The digital world is built on managing massive, sometimes overwhelming amounts of information. And having the right mechanical tools to sort it all out, that literally makes the difference between an application that flies effortlessly and one that just crashes under its own weight. Think about the stark contrast between the physical and the digital for a second. Imagine wasting hours searching through a messy, giant pile of physical CDs just to find one specific track. Now compare that to the 2 seconds it takes to find a song on a modern app. That incredible leap in speed isn't just magic, it's entirely thanks to underlying data organization.
So, what is a data structure? It's simply a specific, specialized way to organize memory. And the golden rule here is pretty straightforward. It is the exact same data, but a different structure yields a massive difference in speed.
We care about this because these structures are the very foundation of modern computing. They enable lightning-fast data manipulation and really form the bedrock of complex algorithms. By optimizing memory usage, they literally save millions in AWS server costs, they preserve your phone's battery life, and they do it all while seamlessly mirroring the physical constraints of our everyday lives. Programming isn't abstract magic. It's honestly more like a digital filing cabinet for physical reality. Think about how a physical line at the grocery store maps perfectly to a digital queue. Your family tree becomes a tree structure, your sprawling social connections are a graph, and your basic daily to-do list, that's just a linked list. Now, to keep our tools organized, we divide them by geometry. We have linear structures, which are the predictable, straight-line sequences of data, and then we have nonlinear structures, the organic, multidirectional geometry of a branching network. But right before you pick a tool, you really have to understand the vital trade-off in memory allocation. On one hand, you have static memory. This is fixed in size at compile time, exactly like a parking lot with a set number of painted spaces. It's incredibly fast, but super inflexible. On the other hand, dynamic memory grows infinitely as needed. It changes flexibly, like adding links to a metal chain during execution. That reduces memory waste, but it can be slightly slower to access. The array is your static workhorse. It offers instant reads by an exact index number, just like opening a specific numbered school locker. If you have a fixed dataset, say exactly 30 test scores, sitting in a continuous row in memory, the array gives you a massive mechanical advantage for instantaneous access. But what happens when your dataset size changes unpredictably? Well, then you need the linked list. This is a dynamic linear tool that uses modular train cars pointing to one another rather than sitting in a continuous fixed row. Imagine a crane dropping a new train car absolutely anywhere on the track. It's perfectly ideal for something like a dynamic music playlist where you want to add or remove songs anywhere in the running order effortlessly. When you need to hit the undo button, you use a stack. A stack enforces last-in, first-out mechanics, or LIFO. Think of a spring-loaded cylinder of cafeteria plates. The most recently added plate on the top is the absolute only one you can remove. It is the exact same logic powering the back button in your web browser. Conversely, to guarantee absolute fairness, we use a queue. This enforces first-in, first-out, or FIFO. It operates identically to a line at a coffee shop or a network printer. The first data to enter the line is guaranteed to be the first one to exit. So, these linear tools are undeniably powerful, but it begs a really crucial question. How do we organize our data when it stops moving in a straight, predictable line and needs to branch out organically into complex webs? For extraordinarily fast data retrieval, we use the hash table. Operating on key-value pairs, it gives us the mechanical advantage of looking up a word in a dictionary rather than reading the entire book cover to cover. You take a key, like the name John Smith, run it through a function, and instantly reveal its value. It is the backbone of nearly every modern database search out there. When you're dealing with strict rank or containment, the tree structure maps hierarchical data perfectly. It mirrors a biological family tree routing from a single root down into branches and finally out to individual leaves. It ensures data is rigidly structured by rank, which is exactly how file system directories nest folders inside of other folders on your computer.
And for the most complex, multi-directional webs where literally any node connects to any other, we pull out the graph. This structure allows for cycle loops and really complex pathway calculations. It is the literal foundation for calculating the fastest GPS navigation routes between cities like San Francisco, New York, and Chicago, or mapping out the billions of connections in massive social media networks. This decision tree concept brings it all together. Asking simple diagnostic questions leads you directly to the right tool. You wouldn't use a hammer for soup, right? If you have a fixed amount of data, you go straight to an array. Need a last-in, first-out operation? Follow the flow directly to a stack. It turns complex architecture into a simple, elegant series of logical choices. And this master taxonomy map proves our initial point. Programming is just categorizing physical realities into linear sequences and nonlinear networks. By using a diagnostic approach, whether you need the static nature of an array, the hierarchy of a tree, or the key value pairing of a hash table, you have a specific, structured answer for absolutely every real-world scenario. Ultimately, matching the right mechanical tool to your data yields a faster program, minimal memory waste, and far cleaner code. We've laid out the entire toolbox for you today, so I'll leave you with this. Looking at the chaotic, fast-paced world around you, what messy, real-world problem will you translate into a beautifully organized digital structure next?